So suppose the specific heat of a gas is given by this particular expression as shown over here, and we have to find out the change in enthalpy when 1 kg of oxygen is heated from the temperature 300 Kelvin to 1000 Kelvin, and that value we have to calculate change in enthalpy in kilojoule per kg. The change in enthalpy is given by mCp delta T. Mass is 1 kg, value of Cp we have written over here. Now let us integrate with respect to T. So integration of 45 into dt, that is nothing but 45 into T. 700 as it is, and integration of 1 upon root T is 2 root T. This 6000 as it is, integration of 1 upon T is log T, and the limits are from T1 to T2. Substitute the limits now. So in place of T, substitute the upper limit minus the lower limit. Similarly, 700 into 2, that is 1400. In place of root T, substitute the upper limit, that is root of T2 minus root of T1 plus this 6000 as it is. In place of this T, again substitute the upper limit, that is log T2 minus log T1, and we know that log m minus log n is log m upon n, so this will be log of T2 by T1. Now substitute the values. The initial value of the temperature T1 is 300 Kelvin and final value of the temperature is 1000 Kelvin. So T2 is 1000 and T1 is 300. The value that we will get over here will be in kilojoule per mole, because this kg, the mass is 1 kg and temperature is in Kelvin. So the value that we will get over here for this mCp delta T will be in terms of kilojoule per mole. Now we want the value in terms of kilojoule per kg. So we'll have to divide this particular value by the molecular weight of the oxygen. And we know that the molecular weight of oxygen is 32 kg per mole. So this mole will get cancelled out and you'll get a proper unit, that is kilojoule per kg. So in this way we can find out this particular enthalpy, that is 551.87 kilojoule per kg. Now let us see another example. In this particular piston cylinder arrangement, it is given that 1 kg of fluid is at a pressure of 25 atmosphere and the initial volume is 0.05 meter cube, and it is allowed to expand reversibly following the process PV raised to 1.3 is equal to constant. So it is a polytropic process and it is allowed to expand in such a way that the volume becomes double. So suppose this is the process over here. So it is expanded in this particular direction. So initial volume is supposed to be V1 and this is the final volume, and the final volume is double than this particular volume. This fluid is then pulled at constant pressure. So this is the constant pressure line, and keeping the piston unaltered, that is, it is a constant volume process. Again the heat is added in such a way that the process is restored back to its original value. So we can show over here the different processes. So this is the polytropic expansion process. Then there is a constant pressure process, and then the constant volume process. So pressure is given as 25 atmosphere. So let us convert that particular pressure into bar. So it is 1 atmosphere is 1.01325 bar. So you get this particular value. Now for the further calculation, again we will have to convert this bar into kilopascal. Now we know that 1 bar is 10 raised to 5 pascal or 10 raised to 5 Newton per meter square, or you can say that 1 bar will be equal to 10 raised to 2 kilopascal. Initial volume that is given is 0.05 meter cube. Final volume is double that of the initial volume, so it will be 0.1 meter cube. Now we know that the given particular process is PV raised to 1.3 is equal to constant. So applying this particular law for the state points 1 and 2, we can say that P1 V1 raised to 1.3 is equal to P2 V2 raised to 1.3. In other words, we can calculate P2. So P2 will be equal to P1 into V1 upon V2 raised to 1.3, and that value again it is in bar, so it is 10.287 bar, because this value we have taken in bar. But for the next calculation, we'll convert this bar into kilopascal by multiplying this value by 10 raised to 2. Now we know that the work done during this polytropic expansion process is given by P1 V1 minus P2 V2 divided by n minus 1, where n is this particular index of expansion, polytropic expansion, and that is 1.3. So substituting all these values, so now you can see here this P1 we have converted from bar into kilopascal by multiplying it by this factor, that is 10 raised to 2. V1 as it is. This P2 also we have converted into kilopascal by multiplying this bar value by 10 raised to 2, and this volume V2 as it is. N is 1.3. So we'll get the work done during this particular process as 79.26 kilojoule. Now as it is an expansion process, this work will be positive. Now work done during the constant pressure process, we know that it is pressure into change in volume. But as the volume is decreasing over here, it is a negative work. So again this pressure P2 is 10.287 bar. We have converted into kilopascal, and volume is from 0.1 minus 0.05, that is V2 minus V1. So there is a compression from V2 to V1, and that work we have considered as negative. The work done during the process 3 to 1 will be 0 because it is a constant volume process. So we can say that the total work or net work done during the cycle will be work done during process 1 to 2, then work done during 2 to 3, plus work done during 3 to 1. So the work done during 1 to 2 is 79.26 minus work done during 2 to 3, it is minus 51.435. So the net work done will be 27.825 kilojoule. Now it is given that the next example, the insulated box is containing some 2.5 kg of gas, and the gas is having specific heat at constant volume as 0.98 kilojoule per kg Kelvin. And it falls from a balloon which is at a height of 5 km above the Earth's surface. And we have to find out what will be the temperature rise of that particular gas when the box hits the ground. Now we know that by virtue of this particular height, the energy that is contained is the potential energy, which is nothing but mgh. So mass is 2.5 kg of that of the gas, gravitational acceleration is 9.81, and height is 5 kilometers, that is nothing but 5,000 meters. Now when that particular box it hits the ground, the entire potential energy will get converted to the heat energy. So according to the law of conservation of energy, this potential energy will be equal to heat energy. And we know that this heat energy at constant volume, so it is mCv delta T. Now substitute the values, so mass is 2.5, Cv that is given, but this is given in kilojoule, so we have to convert this value in joule. So it is 0.98 into 10 raised to 3 joule multiplied by delta T. So this change in temperature we have to calculate. So the value that comes out to be nearly 50.05 degrees centigrade. So in the next example, we are having the monoatomic gas having value of adiabatic index as 1.66 and molecular weight of 40, and is compressed adiabatically from 0.2 megapascal pressure and temperature of 300 Kelvin to 0.4 MPa pressure. The universal gas constant is given in this particular case as 8.314 kilojoule per mole Kelvin, and we have to find out what will be the work done in compressing the gas in kilojoule per kg. Now we know that universal gas constant is 8.314 kilojoule per mole Kelvin. We have to find out the characteristic gas constant, and the relation between the characteristic gas constant and universal gas constant is R is equal to RU divided by M. So universal gas constant is 8.314 kilojoule per mole Kelvin, and molecular weight is always expressed in terms of kg per mole. So this mole will get cancelled out, and you will get the unit of R as 0.2078 kilojoule per kg Kelvin. Now the relation between temperature and pressure in case of adiabatic process is T2 upon T1 is equal to P2 upon P1 raised to gamma minus 1 upon gamma. So therefore T2 will be equal to So substitute these values. So initial temperature is given as 300 Kelvin and pressures are also given. Value of gamma is 1.66. So we'll get temperature is equal to 396.18 Kelvin. Now, in case of the adiabatic process, the work done is given by P1 V1 minus P2 V2 divided by gamma minus 1. Now, in place of P1 V1, we can substitute Mr T1, and in place of P2 V2, we can substitute Mr T2. So, taking this Mr common, we can say that it is Mr into bracket T1 minus T2. So now, substituting the values, we'll get work done is equal to minus 29.83 kilojoule per kg.